Welcome. My name is João Cardoso, and I'll be introducing our paper, Training and Predicting Visual Error for Real-Time Applications. This work has been developed by us at UVM with the help of some NVIDIA researchers. In this paper, we focus on real-time rasterization. In particular, we are interested in recent work that optimizes rasterization by reducing the amount of shading required. For example, this image on the screen is from a paper in 2018 when it was proposed that the amount of shading could be varied across the screen. Each color here represents a different amount of shading using variable rate shading, but with the sole purpose of generating the same image as if variable rate shading was not enabled. So you can think of it as dynamically changing resolution. Other methods have also appeared, such as temporal shading reuse, which is reusing shading from previous renders, and there the question is, when can you reuse the shading from your previous frames? Well, both of these techniques share a common problem, which is, how do you pick, where can you optimize? And that is done using perceptual metrics. Well, the problem with using perceptual metrics in this real-time context is that when rendering, we don't have access to the normal inputs of these metrics. Traditional perceptual error is computed by comparing a degraded and a reference image. But well, if we add the degraded image, we would already have rendered, so we don't have the degraded image before rendering. And if we add the reference image, this optimal rendered image, we would not need to render at all. We already have the frame, the ideal one. So we don't have either of those. How does the existing work solve this problem? Well, they do it by relying on temporal reprojection. So let's consider that we are gonna render a frame. So we have this frame, this is how it would look like. For each pixel on the frame, we could look into the previous render where that surface point corresponds on the screen. If any object or the camera moves, then there will not be a corresponding surface point for each pixel, which means that we end up usually with a result like the image on the right, where the parts of the image have a corresponding pixel in the previous render, but parts are missing. If objects are shiny, then the shading might also change between frames. And this problem will only get worse as more moving parts are in the screen. But nevertheless, existing work takes this temporal reprojection and takes it as a rough approximation of the degraded image before rendering, and then relies on a very fast method to estimate a visual error metric. Let's look at how reprojection actually looks like. Now, in this video, we are seeing a reprojection of the previous render, and when the camera is moving slowly, we won't see any difference. But as soon as the camera starts moving fast, you'll notice that in the edges of the screen, there will be missing render. So now let's actually get into our work. Before we describe our proposed alternative, though, we are planning on using a neural network, so we need to capture some data. So let's just describe the needed setup. First, we look into the scenes we plan to use the method on. Then, we automatically figure out where it's reasonable for the viewer to be in the scenes, and we sample from that random viewpoints. From these viewpoints, we save a lot of screen space information. We pre-render material data and renders at different quality settings. So you can see it in this context that the best quality rendering can be seen as the reference image and lower qualities as different degraded ones. Having done that, we can actually train a neural network with the goal of taking the image space data, including temporal reprojection, and using the convolutional network, having it predict an existing traditional perceptual metric from our choice. To do that, we pre-compute the ground truth metrics using the reference and degraded images, and using a multiple step process that we'll describe later, we use L1 loss between the predicted metric and the ground truth metric to train the network. Just to reiterate, the goal here is that the network will be able to predict any existing metric we choose to train it on. We'll now describe three different things in a bit more detail. First, the image space data, we made some analysis about it, and I will discuss some of the results. And then 2 of the training steps that make this small network be able to actually make these valuable predictions. So first, on the input data, let's consider this shot from a scene, and we'll now look into what the network is capable of predicting for this shot when trained on different sets of inputs. So, if we only use the surface data, as in the top image, we have a prediction for the entire screen. But we're missing information. We don't have lighting information, post-process information. Basically, we know what the surface is, we don't know how it looks like. The temporal reprojection that is used on existing work has the opposite problem, is that it knows how the surfaces look like, or a good estimation how they look like, but does not have a prediction for the entire screen. If we combine both and use all the data we have, we can get the best of both worlds. Yet, using deep lift, we actually made an analysis of the inputs, and we figured out that you can actually cut off a lot of the training input and still obtain great predictions. In particular, throughout this work, we rely only on 4 input channels. We chose these 4 optimal channels from our analysis and gives us as good as a prediction as using all the data. And these are 1 color channel from reprojection and a mask, just be able to tell between missing reprojection and dark regions, a color channel from the diffuse color of the material, and a direction from the view space normals. Alright, now let's look into our training process, because we ran into a problem. Is that this training data we just described is not balanced. We are effectively trying to do regression. And our data is unlikely that it's going to be balanced. Here's an example from a scene where the problems are going to be very obvious because it's mostly background and a very shiny helmet. This means that the training is going to be dominated by background and behavior from the helmet that is very hard to learn. In these scenarios, if you use L2 or L1 loss or other losses that we tried, we end up with very poor results because the network training is dominated by the background, and so the network actually learns very little about the helmet's behavior. And we found a solution, which is to balance the data, we simply take the ground truth metric and transpose it to a space where our training data happens to be balanced. In the paper, we described 2 different transforms to go to this balanced space, and one of them is the faster to compute, that is lossy, and the other one is a bit more expensive, that is lossless. You can do the inverse operation without any losses of information. Now, simply by using this transformed space and L1 loss, we were able to train our network to predict different, well-established perceptual metrics. Flip, ips, and PSNR. Now, I told you a little lie when describing how reprojection has been used to make decisions in existing work. And that is the fact that the reprojection by itself is not enough. And this is because, although the perceptual metric measures how degraded the image is, it does not take into account how likely the user is to notice this error. To account for that, existing work uses the temporal reprojection to estimate a thing called the just noticeable difference, or GND for short, which is a dynamic threshold, which is then compared with the metric to make the rendering decisions, basically of whether the predicted metric is above or below the safe threshold. And now we have a problem, because we went through all of this trouble to have any metric we want across the entire screen, and now we need to use the GND, which is only available where the temporal reprojection is. Okay, we solved this problem by introducing a thing we call the Weber normalization, which is basically do GND in training, not in runtime. We pre-compute the GND using the highest quality rendering we have, the reference image, which is actually better than using the degraded one, it's more precise, and we combined it with the ground truth metric to generate a new metric that already takes into account how likely the user is to notice the error, and thus it can be simply compared with the static threshold to make rendering decisions. Finally, we show on the paper how you can use our network on the variable rate shading use case. This is how it looks. Finally, let's analyze how well our network performs. To do that, we trained on 3 scenes with viewpoints from 3 scenes and evaluate on some others more. We trained on Sun Temple and the Bistro, both in interior and exterior, and then we also tested on the Emerald Square, both at day and night, and in the Siboney Castro. And interestingly, we also tested, of course, forgot, on our Weber normalized variance, our proposed metrics that use the Weber normalization I just described. Interestingly, it performed very well across the board. Furthermore, it actually performed very, very well on the night scene, despite it never seeing this scene during training, nor ever a night scene. All the training data is in daytime, but it still performed very well in the night scene, which leads us to conclude it has generalized very well. What it actually struggles with is shiny materials, which is quite similar to existing work. Because it underperformed in the Bistro interior, the scene with the most shiny objects, despite it being part of the training set. Thank you for your time, I3D, and have a good one.